There are few places in our solar system as mysterious as Jupiter. Recent advances in space observations have unlocked the amazing secrets of this colossal gas giant, buffeted by endless storms and cyclones. Today we're going to talk about some of the recent discoveries made by the James Webb Space Telescope and NASA's Juno mission. A world where storms have raged for more than 3 centuries, where winds penetrate in the most intricate and unexpected ways, and where the largest vortex in our solar system may not be as old as we thought. These discoveries offer a glimpse into Jupiter's complex and dynamic atmosphere. Join us to learn about discoveries that are rewriting the history and understanding of this majestic planet. Let's start with the fact that the James Webb Space Telescope recently discovered unexpected and intriguing shapes above Jupiter's Great Red Spot, a storm that's been raging for more than 3 centuries. These previously unseen structures, observed with the near-infrared spectrograph instrument, have captured the scientific community's attention by revealing the complexity and dynamism of Jupiter's upper atmosphere. At first glance, the atmosphere above the Great Red Spot may seem unremarkable, but the sensitive infrared capabilities of JWST have shown otherwise. Scientists have detected complex patterns, including dark arcs and bright spots, that challenge our previous assumptions. These features are likely caused by a powerful atmospheric gravity wave, a phenomenon in which waves generated in Jupiter's turbulent lower atmosphere propagate upward, altering the structure and radiation of the upper layers. Atmospheric gravity waves are something akin to waves on Earth's beach, which can create ripples in the sand but are much more intense. On Jupiter, they shape the gas giant's upper atmosphere in ways we're only beginning to understand. The tremendous energy and turbulence of the Great Red Spot generate these waves, which then travel upward, affecting the dynamics of the atmosphere. JWST observations have shown that the atmospheric structures over the Great Red Spot consist of different heights, with some regions emitting more infrared light due to the presence of hydrogen in Jupiter's ionosphere. This differentiation in heights and emission is a direct result of the influence of gravitational waves. The region above the Great Red Spot is where Jupiter's lower atmosphere meets its magnetic field, much like Earth's atmosphere meets the solar wind, resulting in spectacular auroras. On Jupiter, this interaction is further complicated by volcanic material from Io, the most volcanically active body in our solar system. These materials, combined with charged particles from the Sun, fuel the Jupiterian auroras and contribute to the complex atmosphere dynamics that we observe. Further study of these gravitational waves is expected to provide a deeper understanding of the energy distribution across Jupiter and enhance our understanding of its atmospheric processes. Future missions, such as the European Space Agency's Jupiter Icy Moons Explorer, or JWST, will build on these findings. Launched in 2023, JWST should reach Jupiter by 2031, where it'll make detailed observations of the planet and its ocean-bearing moons. Another ongoing mission, NASA's Juno mission, has made another groundbreaking discovery. Jupiter's atmospheric winds permeate the planet in cylindrical layers aligned with the axis of rotation. This discovery changes our understanding of the atmosphere and internal structure of the gas giant, disproving long-held assumptions and providing new insights into the dynamics of planetary atmospheres. By analyzing data from the spacecraft's radio signals, scientists measure minute changes in Juno's speed as it orbits Jupiter. These changes, influenced by fluctuations in Jupiter's gravitational field, allow researchers to peer beneath the planet's turbulent cloud cover. Using high-precision measurements, scientists applied a mathematical method commonly used for rocky planets to model Jupiter's gravitational fluctuations. This innovative approach increased the resolution by a factor of 4 over previous models and provided a detailed view of Jupiter's atmospheric winds. The study shows that Jupiter's powerful east-west zonal winds, observed in the planet's colorful belts and zones, do not propagate radially in all directions. Instead, they penetrate in cylindrical layers parallel to Jupiter's axis of rotation. The cylindrical nature of the winds was confirmed by comparing 40 gravity coefficients measured by Juno with theoretical models. This discovery marks a significant advance in our understanding of the atmospheric dynamics of Jupiter and similar planets. The cylindrical structure of the winds suggests a more complex interaction between the deep atmosphere and internal planetary processes. Unlike Earth's zonal flows, which are influenced by surface and topography, Jupiter's winds extend deep into its interior, unaffected by solid boundaries. These winds reach a depth of about 1,860 miles beneath the cloud tops, much deeper than previously thought. This has profound implications for our understanding of the gas giant's internal structure and the distribution of energy within the planet. But let's get back to JWST, whose news flow never ceases. The telescope has once again revealed unprecedented details about Jupiter's atmosphere. This time, researchers have detected a high-speed jet stream passing over Jupiter's equator above the main cloud decks. This jet stream, more than 3,000 miles wide, again updates our understanding of the complex dynamics of the planet's atmospheric layers. Using NIRCam, scientists have detected this jet 12 to 21 miles above Jupiter's cloud tops. The jet has a speed of 320 miles per hour, which is twice the speed of a Category 5 hurricane on Earth. The discovery sheds light on how Jupiter's atmospheric layers interact, revealing the complexity of the gas giant's weather systems. Jupiter, like Earth, has a multi-layered atmosphere. However, the dynamics of the gas giant's atmosphere are much more intense. The newly discovered jet stream is located in Jupiter's lower stratosphere, just above the tropospheric haze. This position allows it to influence the weather patterns and cloud formations we observe in the equatorial region of the planet. By capturing images in the near-infrared wavelength range, JWST can observe altitudinal layers with surprising clarity. These observations revealed several wind shears, areas where wind speed changes with altitude or distance. That allowed researchers to track the motion of the jet stream. The JWST data, taken at 10-hour intervals, one Jupiterian day, provided a detailed snapshot of atmospheric changes. Additional Hubble Space Telescope observations taken one day after the data from JWST played a crucial role in determining the baseline of Jupiter's equatorial atmosphere. While Hubble's observations focused on the lower layers, JWST's near-infrared capabilities provide a detailed look at high-altitude features. This dual perspective allowed scientists to measure how wind speeds change with altitude and reveal the presence of significant shifts. The detection of the jet stream was unexpected, as previous observations by ground-based telescopes and missions like Juno and Ceti had not revealed such detailed features. The researchers intend to continue observing Jupiter with JWST to determine if the speed and height of the jet stream change over time. Lee Fletcher of the University of Leicester suggests that the strength of the new jet may be related to variations in the planet's stratosphere and could change significantly over the next few years. This ongoing study may reveal more information about the cyclical dynamics of the gas giant's atmosphere. Jupiter's Great Red Spot, the largest and oldest known storm in the solar system, has long been a subject of fascination and mystery. Recently, new theories have emerged that challenge our understanding of this iconic atmospheric formation, suggesting that the Great Red Spot we see today may not be the same storm observed centuries ago. In 1665, Italian astronomer Giovanni Cassini recorded a giant dark spot on Jupiter, which he called the permanent spot. This feature, perhaps first noted by English scientist Robert Hooke in 1664, disappeared from observations by 1713. For many years, astronomers believed that the permanent spot was the same as the modern Great Red Spot, first observed in 1831 at the same latitude. However, a recent study led by Agustin Sanchez La Vega of the University of Basque Country suggests otherwise. After analyzing the size and movement of these vortices over time, the researchers concluded that it's highly unlikely that the current Great Red Spot is the same as Cassini's permanent spot. Most likely, the original storm disappeared between the mid-18th and 19th centuries, making the current Great Red Spot a younger formation with a lifespan of more than 190 years. Using historical data, Sanchez La Vega and his team performed computer modeling to figure out how the Great Red Spot might have formed. The leading theory is that wind instability in Jupiter's atmosphere created the elongated atmospheric cell we see today. This process involves a complex interaction between the planet's high-speed winds and the dynamics of its atmosphere. One of the most significant observations of the Great Red Spot is its constant shrinking. In 1879, the size of the spot was about 24,200 miles, and that's along its longest axis. Today, it is only 8,700 miles long. This dramatic decrease in size raises questions about the storm's future. Will the Great Red Spot eventually disappear, as Cassini's permanent spot did? The research team plans to conduct further modeling to predict the fate of the Great Red Spot. These models will help scientists understand whether the storm will eventually dissipate, and if so, whether a new vortex could form in its place, continuing the cycle observed over centuries. The study of the Great Red Spot not only deepens our knowledge of Jupiter, but also provides insight into the behavior of large-scale vortices on other gas giants and even exoplanets. This new perspective highlights the importance of continuous observations and advanced modeling in unlocking the mysteries of our universe. Despite the vast differences between Jupiter and Earth, the dynamics of their atmospheres and oceans reveal surprising similarities. Recent research by physical oceanographer Leah Siegelman has shown that Jupiter's gas cyclones mirror the behavior of oceanic structures on Earth, offering new insights into the underlying mechanisms that govern these powerful systems. Jupiter's atmosphere, often described as an ocean of gas, exhibits cyclonic activity driven by convection, and that's similar to storms on Earth. Convection is the process by which heat is transferred through fluid motion, and it plays an important role in both terrestrial and Jupiter weather systems. On Earth, convection occurs in both the atmosphere and oceans, creating storm fronts and ocean currents. A study by Siegelman, who analyzed data from NASA's Juno spacecraft, has identified filaments, wispy tendrils, between Jupiter's vortices. They behave similarly to fronts in Earth's oceans and atmospheres. These fronts, characterized by boundaries between masses of different densities, are crucial to the generation of strong winds and currents. On Earth, these density differences are usually due to variations in temperature and salinity, whereas on Jupiter they arise from temperature differences in the gaseous layers. By calculating the horizontal and vertical wind speeds of these filaments from infrared images, Team Siegelman confirmed that they contribute significantly to the energy dynamics of Jupiter's cyclones. These filaments help transfer thermal energy from the planet's interior to its upper atmosphere, which accounts for a significant portion of the cyclone's total kinetic energy and vertical heat transport. The presence of convection and fronts on both Earth and Jupiter suggests that these physical mechanisms are fundamental to turbulent fluid bodies throughout the universe. This finding implies that similar processes may exist on other planets with atmosphere or fluid layers, expanding our understanding of planetary science. The comparison of Jupiter's gas cyclones with Earth's oceanic structures provides a basis for the study of other celestial bodies. The ability to draw parallels between such different environments emphasizes the universality of certain physical principles, regardless of specific conditions. The advances in our understanding of Jupiter provided by the JWST and Juno discoveries not only expand our knowledge of the planet, but also set new standards for what can be achieved with advanced space telescopes and probes. High-resolution images and detailed data have revealed previously unseen structures and dynamics in Jupiter's atmosphere. These discoveries pave the way for future missions and exploration. Planned missions such as the European Space Agency's Jupiter Icy Moons Explorer will delve deeper into the Jupiter system, focusing on its moons, Ganymede, Callisto, and Europa. The purpose of these missions? To explore the potential habitability of these moons and further unravel the mysteries of Jupiter's atmosphere. Future space telescopes and probes will have more advanced sensors, enhanced data processing capabilities, and more sophisticated observational techniques, enabling even more detailed and comprehensive studies of distant planets and their atmospheres. By continuing to study the features of this gas giant and its similarities to our home planet, scientists will be able to better predict and model the behavior of the atmospheres of other planets, which of course will expand our knowledge of the cosmos and subsequently help in the search for habitable worlds. The journey is just beginning, so stay tuned as we continue to bring you the latest news and discoveries. There is a phenomenon in the field of astronomy that has intrigued and puzzled scientists for years. Hidden behind the glittering veil of the Milky Way, in the region of space we call the avoidance zone, there exists a gravitational anomaly so vast, so powerful, that it tugs at the very fabric of our universe. This is the Great Attractor. Although invisible to our telescopes, its gravitational influence is so great that it affects the motion of galaxies hundreds of millions of light years away, including our own Milky Way. But what is the Great Attractor? Is it a supermassive black hole? A colossally dense cluster of galaxies? Or something else entirely? And more importantly, what does its existence mean for us, for our galaxy, and for the future of the universe? In this video, we'll explore these questions, delving into the impact of the Great Attractor on our galaxy and the challenges scientists face in observing this elusive region of the cosmos. We'll also travel to the recently discovered South Pole Wall, a vast cluster of galaxies stretching at least 700 million light years into space, and its intriguing connection to the Great Attractor. So, will we eventually be consumed by this anomaly, or does it still serve another purpose in the grand scheme of the universe? Let's find out. About 4 decades ago, astronomers used the Parkes telescope to peer through the dust of the Milky Way. They discovered that our galaxy is traveling through space much faster than expected. Imagine, our Milky Way is traveling through space at 2,500 times the cruising speed of an airliner, 55 times the escape velocity of the Earth, and even twice the escape velocity of the galaxy itself. But where does such movement come from? Here's the mystery. The theory of our origin, based on the Big Bang, tells us that every point in the universe should fly apart from every other point. However, the galaxies on either side of us should be moving at the same recessional velocity, which should not result in net motion in the Milky Way reference frame. Net motion can arise from nearby clusters in the distribution of matter, such as a massive cluster of galaxies. The additional gravitational attraction of such a cluster of galaxies can slow down and even reverse the expansion of the universe in its immediate vicinity. But in the direction of motion of the Milky Way, such a cluster is not obvious. There is an excess of galaxies in the general vicinity and an excess of radiation visible in X-ray telescopes, but nothing that somehow seems large enough to explain the results. So what are we observing? A super density of pure dark matter? Or is the current theory of the origin of mass and motion wrong? Astronomer Alan Dressler of the Carnegie Institution used the first explanation, dashingly calling the missing concentration of matter the Great Attractor. But the mystery of the Great Attractor continues to baffle us. Despite our best efforts and the discovery of new galaxies, galaxy clusters, and new threads in the cosmic web, we still haven't found enough to explain our motion. The Great Attractor remains a mystery, pulling in our Milky Way and leaving us with more questions than answers. So over a vast expanse of space some 220 million light-years away, there is a gravitational anomaly known as the Great Attractor. This region of space, located within the Laniakea supergroup, has such an enormous gravitational pull that it affects the motion of galaxies for hundreds of millions of light-years, including our own Milky Way. But what is a Great Attractor? The term Great Attractor was coined to describe its gravitational influence, but it is not actually a single entity, but rather a region of space with a higher concentration of mass. This mass consists not only of visible matter like stars and galaxies, but also dark matter, an invisible and mysterious form of matter that by some estimates makes up about 85% of the mass of the universe. Understanding the Great Attractor is like putting together a cosmic puzzle. We know it's there because we can observe its gravitational effects, but we cannot see it directly because it's located in the avoidance zone, a region of space hidden by the dust and stars of the Milky Way. Despite these challenges, scientists have made significant progress in studying the Great Attractor. They have used various techniques, such as X-ray, infrared, and radio observations to peer through the dust and gas of the Milky Way and gain insight into this mysterious region of space. According to information to date, the Great Attractor is part of a larger structure called the Norma Cluster, which is one of the most saturated known galaxy clusters. It is in this cluster that the center of the Great Attractor is located. The Norma Cluster is moving toward the Great Attractor at an astounding speed of about 1,340 miles per second. So as we've said, the gravitational influence of the Great Attractor extends over a region of space spanning hundreds of millions of light-years. This region, known to us as the gravity well of the Great Attractor, includes our own local group of galaxies, which is attracted to the Great Attractor at a rate of about 370 miles per second. Observing the Great Attractor is not easy. You can't just point a telescope at it and look. The main problem is its location. The Great Attractor is located behind the Milky Way in a region astronomers call the avoidance zone. The zone is filled with dust and stars, making it difficult to observe the Great Attractor directly. However, it hasn't stopped astronomers from trying to unlock its secrets. They have to be creative in their methods, using different types of observations to peer through the dust and gas of our own galaxy. One of the main methods used is the observation of the 21-centimeter-long neutral hydrogen line. This faint line can be detected by sensitive radio receivers, allowing astronomers to see thousands of galaxies in blind surveys. The advantage of using radio waves is that they can pass right through the dust layer in the Milky Way, making our galaxy invisible. In the late 1990s, a group of astronomers began using the Parkes multi-beam receiver, an innovative instrument located in New South Wales. This receiver's unique sensitivity and field of view allowed increasingly sensitive radio surveys of the sky. These surveys, combined with data from new infrared surveys by the Hubble Space Telescope, have allowed astronomers to confirm the presence of nearly 80% of the galaxies found in the avoidance zone. The remaining 20% are too deep in the Milky Way to be confirmed with any existing optical or infrared telescopes. The zone of avoidance is a fascinating region of space. It's like a curtain that hides part of the universe from our view. But with the help of advanced technology and innovative techniques, we've been able to peek behind this veil and see hidden galaxies. The use of infrared surveys has been crucial. These surveys have allowed us to confirm the presence of galaxies that were previously hidden. It's like having a torch that can illuminate the dark corners of the universe. As we continue to explore and map the universe, a colossal structure known as the South Pole Wall has been discovered in the vast expanse of space. This wall, a veil of galaxies, dust, and gas, extends for at least 700 million light-years. It is so massive that it disrupts the local expansion of the universe. However, this huge structure, like the Great Attractor, remains hidden behind our galaxy, the Milky Way. It stretches from the constellation Perseus to the northern hemisphere to the constellation Apus in the far south. But despite its proximity and size, it's long gone unnoticed, hidden in a darkened sector of the southern sky. The South Pole Wall is a recent discovery announced by an international team of astronomers led by Daniel Pomeroy of the University of Paris Saclay and R. Brent Tully of the University of Hawaii. The discovery was made possible by measuring the distances to 18,000 galaxies 600 million light-years away. Although the South Pole Wall is not visible to us, we can observe its gravitational effects. In an expanding universe, distant galaxies fly away from us. However, galaxies between Earth and the South Pole Wall are moving away from us a little faster than they should be, drawn outward by the huge clump of matter in the wall. Conversely, galaxies beyond the wall move outward more slowly, held back by the gravitational resistance of the wall. The South Pole Wall is an important part of our local universe. It's as large as the Great Wall of Sloan, but is twice as close to us. However, it still goes unnoticed because of its hidden location in the southern part of the sky. It is connected to the larger structure of the Laniakea supergroup, which includes the Great Attractor. All these structures are interconnected, affecting the local expansion of the universe and the motion of the galaxies. The Great Attractor, the South Pole Wall, and other such structures shed light on another enduring cosmic mystery: where we are going. Imagine you're floating down a river in a small boat without oars. The current of the river, like the gravitational pull of these cosmic structures, guides the motion of your boat. No matter how hard you try to control your boat, the current pull is too great, ultimately determining your path and speed. Similarly, our galaxy is like a small boat in a cosmic river, guided by the gravitational pull of massive structures such as the South Pole Wall and the Great Attractor. The future of our understanding of the universe and the Great Attractor lies in further research. Astronomers from Australia are leading several pioneering projects. The 2MTF survey, initiated by Castro, has already made a significant progress. Using the Parkes telescope, this survey calculates distances to galaxies, shedding light on the structure and motions in our neighboring universe. But the research doesn't end there. The upcoming Wallaby study, due to begin later this year, promises to push the boundaries of our understanding even further. Using Australia's advanced CSIRO-SKA Pathfinder, or ASCAP telescope, this survey will allow us to probe deeper into the radio universe. In tandem with these radio surveys, the Australian Astronomical Observatory and ANU are embarking on a new optical survey called Taipan. This project will focus on elliptical galaxies, allowing us to travel to more distant regions of the universe. As research continues, our understanding of the universe is being challenged. Theorists are beginning to question the validity of the space-time metric we currently use to describe the universe. There's even talk of changing the general theory of relativity on large scales. As we look out into the cosmic expanse, we can't help but ponder the future of our universe. What does the accelerated expansion of the universe due to dark energy mean for us, for the Milky Way, for our Great Attractor, for the countless galaxies dotting the cosmic landscape? The universe is not static. It is expanding, and this expansion is accelerated by a mysterious force called dark energy. This force is so powerful it stretches the very fabric of space-time, causing galaxies to diverge from each other. But what does this mean for the future of galaxies and superscales? And what role does the Great Attractor play in this cosmic drama? Despite the expansion of the universe, the Great Attractor continues to exert gravitational influence on the galaxies surrounding it, including our Milky Way. So back to the burning question: will the Great Attractor swallow us up? The answer is no. Despite its enormous gravitational pull, the Great Attractor is not a cosmic monster ready to swallow us whole. As the universe expands, its gravitational influence will weaken. In the distant future, as the expansion of the universe continues to accelerate, galaxies that are currently attracted to the Great Attractor may begin to move away. The gravitational bonds holding the superclusters together will weaken, and these massive structures may begin to disintegrate. The future of the universe is a vast, ever-expanding cosmic sea with galaxies like islands drifting in the cosmic ocean, slowly moving away from each other. The Great Attractor, once a formidable gravitational anchor, will eventually lose its power over the galaxies around it. Have we finally found the answer to one of humanity's oldest questions? Are we alone in the universe? The James Webb Space Telescope may have just brought us one step closer to a revolutionary discovery. Meet K2-18b, a distant exoplanet that has suddenly found itself at the forefront of astrobiological research. Why? Because James Webb discovered something unusual in its atmosphere. Something that could potentially signal the existence of life. Water vapor, methane, and even the rare dimethyl sulfide are not just random molecules. They may be the biosignatures we are looking for, clues that life in some form exists beyond Earth. Armed with the most advanced space technology ever created, James Webb is our new guardian of the galaxy. A telescope designed to peer into the unknown and perhaps redefine our understanding of life itself. So, are you ready to venture into the unknown and dive into the mysterious world of K2-18b? As we venture deeper into space in search of answers to questions that have puzzled humanity for generations, we rely on the eyes of our technological marvels to bring the universe into focus. One such eye is the James Webb Telescope, or JWST. For decades, the Hubble Space Telescope has been our window to the universe, producing images that have both delighted and enlightened us. But even Hubble has its limitations. Meet James Webb, a telescope dedicated to pushing the boundaries of what we can see and understand. One of the most innovative features of the JWST is its cool screen technology. This is no ordinary sunshade. It's a multi-layered engineering genius the size of a tennis court that blocks the heat of the sun, earth, and moon. Why is this important? Because it allows the telescope to cool to incredibly low temperatures, increasing its sensitivity to the faint infrared signals emitted by distant celestial bodies. Infrared observations are crucial for studying exoplanets such as K2-18b. Unlike visible light, which can be absorbed or scattered by space dust, infrared waves can overcome such obstacles, giving us clearer and more detailed images. JWST's ability to make infrared observations is not just an achievement, it is a revolution in the way we study distant worlds. So what discoveries await us when we turn his gaze to K2-18b? Located 124 light-years away in the constellation Leo, this exoplanet is more than just a distant rock. You may have heard of the Goldilocks zone, a term describing the habitable zone around a star where conditions are ideal, neither too hot nor too cold, for liquid water to exist. K2-18b orbits around its parent star, K2-18, in just this zone. But what sets it apart from other exoplanets in similar orbits? K2-18b is not just another rocky planet. It is what scientists call a Hycean world. Hycean worlds, characterized by a hydrogen-rich atmosphere and a surface covered by a watery ocean, represent a new frontier in our search for extraterrestrial life. They offer conditions that may be similar to those around hydrothermal vents on Earth, which are known to support diverse ecosystems. Recent observations by the James Webb Space Telescope have revealed intriguing details about the atmosphere of K2-18b, from water vapor to methane and even potential traces of dimethyl sulfide. The atmosphere of this distant world is a cocktail of elements and compounds that could support life, or at least life as we don't yet know it. The discovery of these atmospheric components has caused a wave of excitement in the scientific community. Researchers are full of excitement and speculation as they ponder the implications of these discoveries for astrobiology and the broader quest to understand the nature of life in the universe. Could this Hycean world with its unique atmospheric composition be the key to unlocking the mysteries of extraterrestrial life? And what might its unique conditions mean for the future of astrobiology? When we venture into the field of exoplanet exploration, one of the most challenging but rewarding aspects is the study of alien atmospheres. K2-18b, with its unique location in the habitable zone and intriguing atmospheric composition, provides a compelling example. While Earth's atmosphere is a mixture of nitrogen, oxygen, and gas impurities, K2-18b is a very different cocktail. This exoplanet's hydrogen-dominated atmosphere with traces of water vapor, methane, and perhaps even dimethyl sulfide is a treasure trove of scientific curiosities. Studying the atmosphere of an exoplanet more than 100 light-years away is not an easy task. It involves a technique called spectroscopy, which analyzes the light from the planet's parent star as it passes through the planet's atmosphere. Different molecules absorb light of specific wavelengths, creating a unique fingerprint that can be deciphered to determine the composition of the atmosphere. The infrared capabilities of the James Webb Space Telescope played an important role in these discoveries. The Mid-Infrared Instrument Spectrograph, abbreviated MIRI, allows for an extended range of wavelengths, allowing it to detect a variety of molecules that were previously elusive. The presence of methane and the lack of ammonia in K2-18b's atmosphere has scientists speculating about the types of life that might exist there. On Earth, methane is often produced by biological processes, and its presence on K2-18b opens up the possibility of life forms that thrive in a hydrogen-rich environment, something we've never encountered before. The composition of K2-18b's atmosphere also suggests the presence of a subsurface ocean. This opens up exciting questions about atmosphere-ocean interactions and how these dynamics might affect the overall habitability of the planet. So could its atmosphere be the key to a new understanding of habitability and life beyond Earth? When we think of life, we often imagine Earth-like environments, but in fact, life exists in environments where we can't even imagine. Studying extremophiles, organisms that thrive in extreme environments, opens up new possibilities for studying life beyond Earth. Deep in Earth's oceans, hydrothermal vents spew hot, mineral-rich water, creating an environment devoid of sunlight, but teeming with life. Extremophiles such as the thermophiles and acidophiles thrive there. challenging our traditional understanding of what life needs to survive. Could such life forms exist on exoplanets like K2-18b? The hydrogen-rich atmosphere of K2-18b offers unique conditions for previously unexplored life. On Earth, certain microbes called methanogens produce methane in an oxygen-free environment. If methane in the K2-18b atmosphere is produced biologically, we may be in a world where hydrogen-loving extremophiles thrive. The study of extremophiles expands the range of conditions in which life can exist. From the acidic rivers of Rio Tinto in Spain to the tundra of Siberia, life on Earth exists in a wide variety of extreme environments. This diversity encourages us to reconsider the ecological limits of extraterrestrial life. The potential for a subterranean ocean and hydrogen-rich atmosphere makes K2-18b an attractive target for studying extremophiles in the exoplanet environment. Perhaps this distant world has its version of extreme life, adapted to such conditions and considering them a name for itself. If extremophiles do exist on K2-18b, what might be their evolutionary trajectory? On Earth, life began with simple, single-celled organisms and evolved into complex forms. Could a similar process occur in other worlds given enough time and the right conditions? One of the most interesting aspects of studying the K2-18b atmosphere is the potential presence of dimethyl sulfide, or DMS. On Earth, this compound is often produced by marine phytoplankton and serves as a potential biosignature. But could its presence on an exoplanet like K2-18b also indicate life? In the Earth's oceans, DMS is produced by phytoplankton and serves many ecological functions. It is a compound that, when oxidized in the atmosphere, can lead to cloud formation. Its presence in exoplanet atmospheres, such as that of K2-18b, could be a game changer in the search for extraterrestrial life. The potential detection of DMS on K2-18b is still being tested. The James Webb Space Telescope's mid-infrared instrument spectrograph is capable of detecting such complex molecules, but confirming their presence requires careful analysis and expert judgment. The discovery of potential biosignatures such as DMS at K2-18b has excited the scientific community. However, like any groundbreaking discovery, it's also sparked a debate that oscillates between skepticism and optimism. The scientific community is divided on the implications of the discovery of DMS on K2-18b. While some consider it a strong candidate for biosignatures, others warn that abiotic processes can also produce similar compounds. The debate emphasizes the complexities and challenges in interpreting exoplanet data. Historically, astronomical discoveries have often been met with skepticism. When Galileo first discovered the satellites of Jupiter, his findings were initially rejected by many. Similarly, the discovery of the first exoplanet in 1995 was met with caution. These historical examples serve as a reminder that skepticism is an integral part of the scientific process. The search for extraterrestrial life doesn't depend on a single molecule or observation. Scientists are looking for a combination of biosignatures to create compelling evidence for the existence of life. Could DMS be a part of a larger puzzle involving other biosignatures like methane and water vapor? The debate's likely to continue until additional data is collected. As technology advances, future missions with even more sensitive instruments may provide the confirmation needed to classify the DMS as a true biosignature. Is DMS the key we have been waiting for in the search for alien life, or is it a distraction that is throwing us off track? Either way, the debate itself is a testament to the ever-evolving nature of scientific research. The James Webb Space Telescope has revolutionized our understanding of exoplanets like K2-18b, but it's just one step in a long journey of space exploration. What lies beyond this monumental mission, and how will future technologies continue to expand our cosmic horizons? The Extremely Large Telescope, scheduled for completion by 2025, promises to be another game changer. With a main mirror diameter of 128 feet, it will be the largest near-infrared optical telescope in the world. Its unprecedented sensitivity could confirm or refute the biosignatures detected by the James Webb Space Telescope. The Large UV Optical IR Surveyor, or LUVOIR, is another mission on the horizon that could complement James Webb's findings. Designed to operate over a wide range of wavelengths, LUVOIR can provide even more detailed atmospheric analysis and potentially obtain direct images of exoplanets. As we target more distant exoplanets, advances in propulsion technology will be critical. Components like ion propulsion and even theoretical methods involving antimatter propulsion could drastically reduce travel times, allowing probes to reach and study exoplanets within a human lifetime. We've previously published a video on the possibility of interstellar travel and the challenges associated with it. As we stand on the threshold of potentially revolutionary discoveries, it's worth pausing to consider the philosophical implications and questions that fuel our cosmic curiosity. What does the search for extraterrestrial life mean for our understanding of existence, and what questions does it pose for the future? One question that's becoming relevant is the role of red dwarfs in the galaxy. Could these numerous stars, often overlooked because of their small size and dim light, actually be the cradle of life? Their longevity and stability make them intriguing candidates for planets that have life. What would the discovery of extraterrestrial phytoplankton mean for our understanding of life? Such a discovery would not only confirm the existence of life beyond Earth, but would also suggest that the building blocks of life are more universal than we thought. What will the next decade reveal in our quest to understand the cosmos? Will we confirm the existence of extraterrestrial life? Or will we discover new, even more complex questions that challenge our understanding of the universe? Approximately 13.8 billion years ago, a singularity, an entity of infinite density and gravity, arose that quickly swelled and cooled, giving birth to our universe. This event is known to us as the Big Bang. However, speculation about such things does not provide answers, but only generates more and more questions. What was there before the Big Bang? Is there even a before in the universe, where time itself was born out of this primordial explosion? Are we the last chapter in an endless cycle of cosmic death and rebirth? The greatest minds of our species have proposed theories, each as mind-boggling as the next. Some speak of other universes, while others postulate a universe that breathes, collapses, and expands in an infinite cycle. Let's try to make sense of what actually happened before the beginning of time itself. Imagine a universe that breathes. It expands outward from one point, grows for billions of years, and then shrinks, drawing in all matter and energy. This is the essence of the oscillating universe theory. This model assumes that our universe is just one phase in an endless cycle of expansion and contraction, a cosmic dance that has neither beginning nor end. Each cycle begins with the Big Bang, an explosive moment of creation followed by a long period of expansion. Over billions of years, this expansion slows, stops, and then reverses. The universe begins to contract, which eventually leads to the Big Crunch. During the Big Bang, galaxies collide, stars are compressed, and all matter and energy is squeezed into a singular point of infinite density. very similar to the singularity from which the Big Bang occurred. But this is not the end, but the beginning of another cycle. The singularity explodes with another Big Bang, starting the next iteration of the universe. The lifetime of each universe in this model could be billions, even trillions of years, and each Big Bang prepares the ground for the next Big Bang. It's a fascinating concept, isn't it? Like a cosmic pendulum swinging back and forth between expansion and contraction, destroying and recreating universes in its path. However, the theory of an oscillating universe is not without flaws and criticisms. We've yet to understand many factors concerning the expansion of the universe, its exact energy composition, and how gravity behaves on such scales. And the data we've collected from the cosmic microwave background seems to point to an ever-accelerating expansion, not a possible future contraction. But as always, science continues to evolve, and once rejected theories might find new life in the light of new discoveries. Throughout our exploration of space and time, we've always thought of our universe as unique, a single bubble of reality floating in an endless sea of nothingness. But what if we are not alone? What if our universe is just one of an unimaginable multitude of other universes, each with its own laws of physics, its own history, its own beginning and end? This is the premise of the multiverse theory. Imagine a vast cosmic ocean in which countless bubbles appear and disappear. Each of these bubbles represents an independent universe, and our universe is just one of them among this cosmic foam. Some of these universes may be different from ours, have different physical constants, or even other dimensions. Others may be strikingly similar and may even contain life as we know it. What if some of these universes preceded ours? Could our Big Bang have been caused by an interaction with another universe? The multiverse concept challenges our understanding of our place in the cosmos. Nevertheless, it is a theory that remains highly speculative. While the multiverse theory is fascinating, it is also controversial. After all, if these other universes are beyond our reach, how can we detect or study them? And if the theory cannot be tested, can it be considered scientific? Nevertheless, multiverse theory continues to be the subject of research and debate among physicists. It represents the edge of our understanding, where science mixes with philosophy, and observable facts give way to profound questions about the nature of reality itself. And yet, despite the supposed multiplicity of universes with all their variety of physical forces and dimensions, let us return to the realities of ours. Our understanding of the universe rests on two pillars of modern physics: quantum mechanics, which describes a world on the atomic and subatomic scale, and general relativity, which describes a world of very large dimensions. But what happens when these two worlds collide? According to Einstein's general theory of relativity, space and time are interwoven into four-dimensional fabrics known as space-time. Massive objects distort this fabric, creating what we perceive as gravity. On the other hand, quantum mechanics presents a world in which particles can exist in several states simultaneously, appear and disappear. It is a world that challenges our everyday logic. These two theories meet in the singularity of the Big Bang and in the heart of black holes, where the scales of quantum mechanics and gravity intersect. Scientists have long sought a theory of quantum gravity to reconcile these two conflicting views. One exciting idea that emerged from this search is the no-boundary proposal, championed by physicists Stephen Hawking and James Hartle. According to this theory, the universe did not emerge from a singularity. Instead, space and time are finite, but limitless, like the surface of the Earth. Just as you can travel the Earth without falling off the edge, you can travel the universe without colliding with a boundary. The universe would be a four-dimensional sphere, and the Big Bang would be a smooth point similar to Earth's North Pole, but not a singularity. In this model, asking what happened before the Big Bang becomes as meaningless as asking what is north of the North Pole. This is a pretty good way to get around the singularity problem at the beginning of the universe. Like the other theories we've discussed, the no boundaries proposal is not without criticism and is still the subject of ongoing research. Nevertheless, it represents an intriguing attempt to bring together worlds incredibly large and incredibly small, pushing the boundaries of our understanding of the origin of the universe. Now let's look into the field of string theory, a theoretical framework in which the fundamental building blocks of the universe are not particles but one-dimensional entities called strings. Each string can vibrate at different frequencies, and these different vibrations produce different particles. Electrons, quarks, photons, all of them can be strings just singing on different notes. But string theory doesn't stop there. It also predicts the existence of more than 3 spatial dimensions with which we are familiar. These additional dimensions may be compacted or hidden from our perception, but nevertheless fundamentally affect the fabric of reality. In the context of our topic, one variant of the string theory, the pre-Big Bang scenario, or as it's also called, the ekpyrotic model, suggests that our universe may have been created by the catastrophic collision of 2 multiverse worlds or brains. What happens after such a collision? The 2 brains bounce off and apart only to come together gravitationally and collide again billions of years later, perhaps creating another universe. So what was there before the Big Bang? Well, in this model, it could have been another universe similar to ours, existing on a brain parallel to ours. And yet, string theory itself, although incredibly elegant and capable of combining quantum mechanics and gravity, has no empirical evidence. And as we already know, such things are very difficult to verify. But what if we choose a different approach? Instead of looking for a universe that preceded ours, what if we reconsider the very notion of nothingness? When we think of a vacuum, we often imagine absolute nothingness. But in the world of quantum mechanics, the vacuum is far from empty. This is a bubbling soup of particles and antiparticles that spontaneously arise and then destroy each other. This phenomenon is called vacuum fluctuations. The vacuum fluctuation model, also known as the quantum fluctuation model, suggests that our universe may have originated from one of these vacuum fluctuations. A tiny bubble of false vacuum could have inflated into the universe due to the principles of quantum mechanics. Such a bubble, due to phase transition or quantum tunneling, would begin to expand rapidly, and its edges would be pushed outward by negative pressure. Inside this bubble, false vacuum energy could be transformed into matter, giving rise to stars, galaxies, and eventually, you and I. So, what was there before the Big Bang? In the vacuum fluctuation model, it could have been a quantum vacuum, a sea of short-lived particles and antiparticles, and our universe was just one random bubble that managed to grow into something bigger. Now, while the vacuum fluctuation model is an exciting possibility, it also raises difficult questions. For example, why did this particular bubble expand while others did not? And how do we reconcile the idea of an eternal quantum vacuum with the apparent age of our universe? But as we delve deeper into the world of quantum physics, we find that it holds more intriguing possibilities. One of these possibilities is related to the field of research that combines quantum mechanics with cosmology. That brings us to the next model, the Big Bounce theory. Imagine a universe that expands, contracts, then bounces back elastically. That's the basic idea of the Big Bounce theory. Instead of a singularity in which all the laws of physics cease to exist, the Big Bounce theory argues that our universe may have been born from the remnants of an earlier contracting universe. In this model, the universe is not compressed into singularity. Instead, because of quantum effects, it returns to a very small size and begins to expand again, leading to what we now call the Big Bang. This theory, like the oscillating universe theory, postulates a universe with no beginning and no end, but with an infinite cycle of expansion, contraction, and rebirth. In this way, it circumvents the singularities that plague the other models. However, unlike the oscillating universe theory, the Big Bounce focuses specifically on the transition point, the bounce between contraction and expansion. So how does quantum mechanics fit into this? Quantum effects are thought to play a significant role on the very small scales at which rebound can occur. According to quantum mechanics, particles can tunnel through barriers even if they have no classical energy to do so. Some theories suggest that the universe could use a similar quantum tunneling effect to bounce from a contracting state to an expanding one. Again, this theory is highly speculative and faces significant problems, both theoretical and observational. Can we find evidence for a previous phase of contraction in our present universe? Can we develop a quantum theory of gravity that can handle these extreme conditions? However, the Big Bounce theory is not without its flaws. The physics of what can make the shrinking universe come back to normal is still being investigated. Understanding how this process can occur without violating the known laws of physics is the main obstacle to this theory. The Big Bounce theory does not yet fit within our traditional notions of time and causality. However, as always in science, there are competing theories. For example, our universe could have been born from a cosmic object that we have already discovered but barely understand. Something mysterious, all-consuming, but perhaps also creative. A black hole? Black holes, mysterious giants of the universe, formed by the collapse of massive stars. They are regions of space where gravity is so strong that nothing, not even light, can leave it. The base of a black hole, according to the general theory of relativity, is a singularity, a point where density becomes infinite, and the curvature of space-time reaches an extreme degree. But what if these cosmic entities are not the end, but rather the beginning? Some physicists speculate that singularities inside black holes could give rise to new expanding universes. Thus, our universe could be the inner part of a black hole belonging to another parent universe. In this model, the Big Bang would correspond to the formation of a black hole singularity in the parent universe, and the expansion of our universe corresponds to the internal growth of the black hole. So, what was there before the Big Bang? It could be the inside of a black hole in another universe. And maybe every black hole in our universe can give birth to a new universe inside itself. Of course, this idea, like all those we've discussed, is a hypothesis and not without problems. How can we test this theory? Can we observe the effects of the parent universe? And how do we reconcile this with our current understanding of black holes and singularities? Loop quantum gravity, or LQG, is a theoretical framework aimed at reconciling the two giants of 20th century physics: quantum mechanics, which describes the very small, and general relativity, which describes the very large. Loop quantum gravity implies that space itself is not continuous, but consists of tiny, discrete loops. It consists of tiny, indivisible loops, just as a piece of fabric consists of interwoven threads. Applied to cosmology, loop quantum gravity, or more exactly, loop quantum cosmology, offers a rebound scenario similar to the Big Bounce, which we discussed earlier. In fact, loop quantum cosmology provides a specific quantum mechanical description of the universe's evolution, including the Big Bounce scenario. Instead of collapsing into a singularity as required by traditional Big Bang theory and general theory of relativity, the universe shrinks to a minimum size, but quantum gravitational effects become significant and counteract the contraction. Then the universe bounces back and begins to expand again. This means that our universe may have undergone a series of expansions and contractions, each of which began with a quantum jump. So, what was there before the Big Bang? From the point of view of loop quantum cosmology, it may be another phase of the universe, the contraction phase, which preceded the quantum jump. In loop quantum cosmology, the idea of a quantum bridge is truly fascinating. This bridge represents a transitional phase connecting our universe with its predecessor. Instead of singularity, the universe undergoes a quantum leap and starts expanding. This jump, this transformation from contraction to expansion, can be seen as a quantum bridge from the old universe to the new one. This quantum bridge is not a physical bridge in the conventional sense, but a phase of the evolution of the universe controlled by quantum gravity. So what is beyond the Big Bang? According to loop quantum cosmology, the previous universe is connected to ours by a quantum bridge. Although this theory eliminates the singularity at the Big Bang and offers an elegant quantum description of the evolution of the universe, it still faces considerable difficulties. Nevertheless, if it is correct, it offers us an amazing picture. A universe with no beginning and no end, experiencing infinite cycles of contraction, jumping, and expansion. Although these theories offer intriguing possibilities, for the most part they are still in the realm of speculation. Each has its strengths, its weaknesses, and none of them yet has conclusive experimental evidence in its favor. Even as we approach the answer to what was before the Big Bang, we should expect that each answer will open up even more questions. But the beauty of science lies in the process of exploration and discovery itself. Researchers around the world tirelessly study these theories and improve their models. And the study of even one theory goes a long way towards advancing the whole picture. So, what happened before the Big Bang? In a nutshell, at this point, we don't know for sure. But whatever the answer, the search itself enriches our understanding and inspires us to keep looking. In the vast expanse of space among countless stars and galaxies, there is a whisper, the whisper of a distant star that's traveled light years to reach us here on Earth. This is not a science fiction tale, but a reality of our universe, a testament to the continual growth of our understanding of the cosmos. Scientists eavesdropping on space have detected a signal, a radio wave, from a star system not so different from our own. A star known as YZ Ceti is located just 12 light-years away. But it's not just any signal. This signal carries a potential signature of a magnetic field very similar to the one that protects our own planet. The magnetic field that may envelop a rocky Earth-sized exoplanet orbiting YZ Ceti. What could it mean? Could this distant world be more like our own than we've ever imagined? And what could it tell us about the search for life beyond our solar system? Let's go light years across to delve into the mysteries of radio signals in space and explore the magnetic fields of distant worlds. In the boundless silence of space, radio signals can, without guile, be called whispers. But what are these signals and how do they propagate over such vast distances in space? Radio signals are a type of electromagnetic radiation, just like light, X-rays, or microwaves. They're generated by a variety of sources, from stars and galaxies to artificial satellites and spacecraft. These signals travel at the speed of light, carrying information across vast distances in space. They can tell us about the composition of stars, the presence of planets, and even the origin of the universe itself. But how do we detect these signals? The answer lies in the technology of radio astronomy. Radio telescopes, such as the Very Large Array in New Mexico, or the now-defunct Arecibo University in Puerto Rico, are designed to detect and analyze radio signals from space. They are our ears to the cosmos, listening to the faint whispers of the universe. Once a signal is detected by a radio observatory, it is analyzed using sophisticated algorithms and computer models. These analyses can provide extensive information about the source of the signal, from its location and distance to its physical properties. But radio signals from space are not just a scientific curiosity. They also have practical applications. For example, radio signals from satellites are used for GPS navigation, weather forecasting, and Earth observation. They are an integral part of our modern technological infrastructure. So, the next time you look up at the night sky, remember, there's a whole symphony of signals playing out there, a cosmic conversation, an orchestra that we're just beginning to understand. Let us return to the constellation of Cetus, the sea monster, in which lies a star that whispers to us across light years. Her name is YZ Ceti. YZ Ceti is a red dwarf, smaller and cooler than our Sun. It is located 12 light years away, a close neighbor on a cosmic scale. But what makes YZ Ceti truly fascinating is not the star itself, but what revolves around it. At least 3 exoplanets are known to orbit around YZ Ceti, the innermost of which, YZ Ceti b, is of particular interest. YZ Ceti b is a rocky, Earth-sized exoplanet that orbits very close to its parent star. In fact, it is so close that its year, the time it takes to make one revolution around YZ Ceti, is only 1.6 Earth days. Recently, using Very Large Array, scientists at Bucknell University, Professor Jackie Villadsen, and her colleague J. Sebastian Pineda, detected a repeating radio signal coming from YZ Ceti. The signal was recorded at a frequency of 2 to 4 gigahertz. It appears to be modulated by the rotation of the star and the orbit of YZ Ceti b, indicating an interaction between the star and the magnetic field of the planet. This discovery could have major implications for our understanding of exoplanets and their magnetic fields. Although YZ Ceti b is unlikely to be teeming with life due to its close proximity to its star, the detection of its magnetic field is important because it provides a method for discovering more life-friendly worlds in the future. But what does this signal really mean? And why are magnetic fields so important in our search for life? To answer these questions, we need to look deeper into the invisible force fields that shape our universe. Magnetic fields are a fundamental force of nature. They guide the hand of the compass, help birds navigate their long migration, and protect our planet from the harsh solar wind. But magnetic fields are not just an earthly phenomenon. They also play an important role beyond the Earth. Our Sun, for example, has a complex and dynamic magnetic field. It controls the Sun's activity from the formation of sunspots to the eruption of solar flares. Magnetic fields also shape the structure of galaxies, directing the movement of interstellar gas and influencing the formation of new stars. But perhaps the most intriguing role of magnetic fields in space is their potential impact on planetary habitability. A strong magnetic field can protect a planet from harmful radiation from its star, helping to maintain a stable atmosphere, and perhaps even conditions suitable for life. That's why it's so interesting to detect a potential magnetic field on exoplanet YZ Ceti b. This could provide valuable information about the planet's atmosphere and its potential to support life. How do magnetic fields affect the detection and interpretation of signals from space? To understand this, we need to delve a little deeper into the nature of radio signals and magnetic fields. Radio signals are a type of electromagnetic wave, which means they are composed of oscillating electric and magnetic fields. These fields can interact with other magnetic fields they encounter as they travel through space. When a radio signal passes through a magnetic field, it can be altered in various ways. Its direction can be changed, a phenomenon known as deflection. Its polarization, or the orientation of its electric field, can be rotated. Its frequency, in other words, the number of waves passing through a point in a given time, can be shifted. These changes can provide valuable information about the magnetic field that caused them. By studying these changes, scientists can infer properties of the magnetic field such as its strength and orientation. But magnetic fields can also pose problems for detecting signals from space. They can cause interference, making it difficult to detect the signal. They can distort the signal, making it difficult to interpret. This is why the study of magnetic fields is so important in the field of radio astronomy. By understanding how magnetic fields affect radio signals, scientists can develop methods to correct these effects and extract valuable information hidden in signals from space. To better understand the influence of magnetic fields in creating favorable conditions for life on the planet, let's turn our gaze closer to home, to a familiar red-headed neighbor in our cosmic backyard. Mars, the red planet, has long captured our imagination. With its towering volcanoes, deep canyons, and hints of liquid water, it is one of the most intriguing places in our solar system. But Mars also presents us with a mystery. Unlike Earth, Mars has a very weak and inhomogeneous magnetic field. This has serious implications for the planet's atmosphere and its ability to support life. Mars' magnetic field is not created by a dynamo in its core like Earth's. Instead, it's the remnants of magnetism trapped in the planet's crust from the time when Mars actually had a global magnetic field. Without a strong magnetic field protecting it, Mars's atmosphere is directly exposed to the solar wind, a stream of charged particles emitted by the sun. Moreover, new models presented by R. Sakata of the University of Tokyo and others suggest that a weak magnetic field like Mars after its dynamo is turned off could actually lead to a more rapid loss of atmosphere than if there were no magnetic field at all. Modeling has shown that a weak magnetic field results in the fastest rate of atmospheric ion loss, 6 times faster than without a magnetic field. The reason is that the weak magnetic field strength lines were easily repelled by the solar wind, creating a path for ions to escape into space over the night side of Mars. This suggests that Mars' remaining magnetic field may have hastened the planet's transformation into the cold and barren world it is today. Over billions of years, this caused Mars to lose much of its atmosphere, a process known as atmospheric stripping. This turned Mars from a potentially warm and wet world in its early history into the cold and dry planet we see today. The case of Mars provides a vivid illustration of the importance of magnetic fields to a planet's habitability. It shows us that without a strong magnetic field, a planet, even one as Earth-like as Mars, can lose the things that make it habitable: atmosphere and water. By the way, we've already looked at the problems and potential solutions to Mars, a second home for humanity, in a separate video. Exoplanets, planets orbiting stars outside our solar system, have recently become a major focus of astronomical research. With more than 1,000 discovered to date, they offer a wealth of opportunities to learn about the diversity of the planetary systems in our galaxy. One of the most exciting developments in this field was the discovery of the first known magnetic field on an exoplanet in late December 2021 by an international team of astronomers who used the Hubble Space Telescope for their research. It was discovered on a Neptune-sized planet called HAT-P-11b. HAT-P-11b is located about 123 light-years away in the constellation of Swan. It is a hot Neptune, a type of exoplanet that's similar in size to Neptune, but much closer to its star, resulting in high temperatures on the planet's surface. The detection of a magnetic field on HAT-P-11b was a groundbreaking discovery. It showed that exoplanets can generate magnetic fields just like planets in our solar system. As we mentioned earlier, studying the magnetic fields of exoplanets can provide valuable information about their internal structure, atmospheric properties, and potential habitability. For example, a strong magnetic field can protect a planet's atmosphere from stellar winds, helping to preserve conditions that could support life. That brings us back to YZ b, an exoplanet from which a signal was recently detected. If this signal is indeed indicative of a magnetic field, it could have a major implication for our understanding of this exoplanet and its potential for life. Traveling through space from the familiar landscapes of Mars to the far reaches of YZ, we've truly come to realize the invisible power of magnetic fields, their profound effect on planets, and their potential to harbor life on them. The field of studying signals from other galaxies has grown rapidly over the past few years. For example, the giant Microwave telescope in India has detected a faint signal from the most distant galaxy to date. The signal detected by YZ Ceti opened another new window into the universe, reminding us how much we still have to learn about our world. As we look to the future, the study of signals from other galaxies will continue to be the focus of space research. Each signal carries the potential for new discoveries. So when we look up at the night sky, let's remember that we're not just looking at stars and galaxies. We're looking at a universe filled with unseen forces, whispered signals, and hidden possibilities. And as we continue to listen and explore, who knows what we might discover next?